But now I'd like to introduce Curtis, who will show us d3-random. Curtis is a longtime Meetup member, first-time speaker, so be nice.
Right. Thanks everyone for coming. I just wanted to share some things I learned while walking through d3-random and teaching myself some concepts related to it. So just a little bit about me. I'm Kurt Mitch on Twitter. I do have some blocks, like any good side projects. Some are more complete than others, but I've used some of these as examples tonight. I studied math and physics in school and worked as an analyst for several years before catching the data viz bug and wanting to switch into web development. So I've been doing that for about 5 years now, and I'm currently at Mode Analytics, building a web platform for querying your own databases. Some of my teammates are here tonight, and we're always hiring, so feel free to talk to them if you're interested. So why might someone need random data? If you're building any kind of visualization and you don't have the data you're going to be displaying just yet, random data is always a good way to kind of get something off the ground. So tonight we're going to be talking about three main things: different types of randomness in the context of computer science and statistics itself. Then we'll walk through the different methods within d3-random. And then we'll, at the end, kind of touch on a few related concepts within statistics that these different distributions kind of help visualize. So one of the fathers of computer science, John von Neumann, said that anytime you're using software to create a random number, you're inherently in a state of sin. And what he meant by that is that you're using something inherently deterministic to create something that's inherently random, and these don't really go together at all. You can get random numbers with software, but you actually need hardware to do something like a photo detector or a Geiger counter. And you really only want to use these if you're probably doing some hardcore scientific research or deep cryptography. So anytime you are wanting to create a pseudo-random number, you use this class of algorithms called pseudo-random number generators. And these are basically something that take what's called a random seed, and that's usually a string or some kind of state in your computer, and that helps these algorithms kick off the process of creating a random number. For JavaScript, we are all probably familiar with math.random. And this is a unique kind of method in that every time you call it, it's going to give you a different type of number. According to the ECMAScript spec, it's kind of up to the browser or node environment how that random seed gets created. Sometimes it's the computer's clock, it could be the DOM state, but sometimes you want a more predictable type of random number. Say if you're doing testing and you want to remove certain types of unknowns. So the d3-random module has this extension called the random.source. And I'll show in a second how this gets used, but the main idea is that you use some kind of third-party random seed generator to pass in a string, and anytime that'll get used, you'll have a pseudo-random number, but you'll get it in a predictable fashion. So let's see how this works. So this is an example using a module called seed random. There's several different JavaScript random number generators using a seed. And you can see here that every time you declare it, you'll get a random number once you call this generator. But anytime it's redeclared, you'll get the same sequence of random numbers over and over. So you can see why this might be good in a testing situation. And actually, if you look at the d3-random spec files, you'll see this used all over the place. So now let's get on to the core of the d3-random itself. So these are the 6 main distributions that are currently in the d3-random module. And the main thing I wanted to demonstrate with this slide is just to show you the general shape of what these different distributions have. So you can see the uniform's kind of flat. The normal, Bates and Irwin-Hall have this nice curve to them. The log, normal, and exponential kind of have this quick slope. There's a couple different statistical concepts we need to go over before we actually get into how these different generators work themselves. So we're probably all familiar with max and min numbers. This is kind of just telling you the range of values that your random number generator is going to occupy. Something that's a little more complicated is the concept of a random variable. And this is some kind of number that has a random output, but you can say something definitive about what values it's going to occupy. So if you think about a die roll, which is a quintessential example for probability and statistics, a random variable would be the outcome of that die roll. You know it's going to be the numbers, some number between 1 and 6, but you don't know which of those it's going to be exactly. And the expected value is what you expect on average the random variable to be. So for a die roll, it's going to be between the numbers 3 and 4, which is kind of weird in the sense that a die can't actually get to 3.5, but it still tells you something informative about what these numbers can be. So getting a little more complicated in describing random numbers, the next thing we want to do is describe deviation. So here I've created some arbitrary points with no units. And this line kind of represents what we expect these values to be. So this is something you probably see on a regression chart, for example. The deviation just tells you how much these points would deviate from the expected value. So the mean of this deviation we can see is 0.8 for these particular values I have here. Now the variance is a little more complicated, but helps us get to something more informative. And all we're going to do now is square each of these deviations and then divide them by the total number of values we have. You can see that this value comes out to 9. If these had units to them, like feet or miles, this would be something like 9 feet squared, which is hard for humans to relate to. So in that case, we take the standard deviation, which is just the square root. So we can say now that the standard deviation for this set of points is 3 feet or 3 miles or what have you. So let's talk about politics. Imagine that your team or your client or what have you has asked you to make some kind of dashboard for an upcoming campaign. Why might you want to use the random distribution to practice building out that dashboard? Well, you might use this for anything where you want kind of equal outcomes across some series. So say you want all the volunteers in some neighborhood to knock on an equal number of doors. Well, random uniform might help you display that. So it's definitely the most simple of any of these. And usually when people think of random values, this is kind of inherently what they're thinking about. It's some range of numbers where all outcomes are equally likely. So as you can see here, you pass in a max and min, which default to 0 and 1, which is what the math.random method does itself. And in this case, the expected value would just be the average of these two inputs. The more complicated version is going to be random normal. And we'll see towards the end of the talk why this comes up so often, but one example you might think of for our politics dashboard might be doing many, many simulations of voting outcomes. And you'll see towards the end why this tends to assume a normal distribution shape. So the arguments for this are more complicated than just the min and max. These go back to the expected value and the standard deviation, which in math notation are mu and sigma. So these also default to 0 and 1, but whereas the uniform distribution was occupying values between 0 and 1, using these default values gives you some spreads centered on 0. And you've probably seen a visualization like this before, which shows you how the points in this distribution start to lay out within different values of the standard deviation. So the typical rule of thumb is that one standard deviation, 95 within 2, 99.7 within 3. And unless you're trying to find maybe the Higgs boson, you probably don't need to go beyond that. So one common visualization you might see related to politics is this one. So you can see that this assumes a normal shape across many different types of election outcomes. So this was a 538 New York Times simulation of the 2016 election. And again, we'll get towards the end of the talk to describing why this assumed this shape. And the last one I want to talk about in our politics example is the random log normal. So in most cases, I think when people are using random data, random uniform and random normal is most likely what they're going to be using. And the rest of these distributions will get maybe less and less likely to be applicable in your case, but still worth going through. And the random log normal is pretty much what it sounds like. What it's saying is that it's some distribution where the log values of this range assume a normal shape. So it also takes in sigma with defaults of 0 and 1. And it's essentially, if you look in the source code for it, assumes the shape of math.exponent raised to the random normal outcome. Because of the way these numbers behave, this is why we have such a strong drop off of the distribution. So now we're going to switch gears slightly. And instead of politics, let's assume we're making a dashboard for some sort of manufacturing firm. So we're making widgets. We want to display some values that tell us the state of these widgets and the lifetime of them. So the fourth distribution rather that I want to talk about is the random exponential. And even though this has a pretty similar shape to the log normal, it has a pretty different way of getting computed. So this argument, unlike the standard deviation and expected value, is what's called a lambda, and it's using the concept of a Poisson process. What this means is that it's some kind of outcome that it's a concept rather where you're saying that some event is going to happen within a specific moment in time. So for this example I made up in the upper right, I passed in a value of lambda equals 5. What that means is it's just 5 of some unit of time. So 5 minutes, 5 years, what have you. But I'm expecting some event to happen once in that period of time. So maybe for our widget calculation or widget dashboard, I might think that the lifetime of this widget is going to be 5 years. So if I use the exponential distribution, I can see where I expect this widget to break down within that 5-year time span. So again, the log normal has a much steeper curve. The exponential is a little more sloped. Now, these last two are pretty esoteric, and when I started exploring the random module, I had no idea what they would be used for. I found out that one applicable case for the Bates distribution, say in this manufacturing example, might be the following. So say we have a little more complicated data about our widget. It has maybe 3 different points in its lifespan. So say it's maybe on a car, for instance, and you have some life cycle moment where it occupies the first 50,000 miles of the car, the next 50,000, and so on. The Bates distribution can be used to tell us what you expect the average length of time within those different lifespans to be, which is a little weird, but bear with me. So it's named after American mathematician Grace Bates, who was one of the first women to get a mathematics PhD in the 40s. This distribution is comprised of the means of a number of independent, uniformly random variables. And I'll show a visualization shortly of what exactly that means. But basically, it's taking the mean of the outcomes of these different uniformly random distributions. And that's what you pass in as the argument here. Now, the random Irwin-Hall is similar. This one is named after these British mathematicians, Joseph Oscar Irwin and Philip Hall. It's comprised of the sum, not the mean, of a number of independent uniformly random variables. So it's also known as the uniform sum distribution. And again, it takes the same arguments and the number of random variables. So jumping out real quickly, let's look at how these behave. So as I said before, these two distributions are made up of uniform random variables. So I'm passing in n here, but if I lower this to 1, you'll see it looks like a uniform distribution. But the more I go up, the more it starts to assume a normal shape. So at 2, it kind of resembles a triangle, and then it'll start to assume a more uniform looking shape. And the same goes for the Irwin-Hall. If I drop back down to 1, it looks again like a uniform distribution. And the more I go up, it goes from triangle to maybe assuming a nice curve, but with random numbers, you never quite know what you're gonna get. Okay. So if tomorrow you're kind of summarizing this talk to somebody and you're trying to remember whether the Irwin-Hall was the mean and maybe Bates was the sum, don't feel too bad about this because Mike Bostock himself confused them and had to correct this error a couple years ago. So there's 2 big ideas from statistics that I want to just touch on because I think they're pretty fascinating, and these distributions kind of go a long way to visualizing these ideas. So the first one is called the law of large numbers, and this is an intuitive idea once you look at it closely. So all it says is that the more experiments you perform, the closer your results are going to get to the expected variable. If I do die roll after die roll, I'm eventually going to get an average outcome of 3.5. So, and I made another block that kind of demonstrates this. So here I just have a histogram of 100 random uniform outputs. So you expect the height of each of these 20 columns to be 5 each. You can see at just 100 that there's pretty wide variation between the heights of these columns. But the higher I go, and you have to go significantly higher before you start seeing these outcomes, you'll see that they start to get closer and closer to the red line that resembles or represents the expected value. Maybe at 5,000, get a little bit closer, and so on. And so the other big idea I want to touch on is called the central limit theorem. And this really comes up all the time once you start getting into probability and statistics. And as I alluded to before with the political examples, the reason this comes up so often is because of how powerful it is. And it says that the sum of any large number of random variables assumes an approximately normal shape. So this is why statisticians can go out and interview small groups of people all over the country about who they're going to vote for and start to build something that resembles the uniform distribution. And this blew my mind the first time I realized it, but this is why the Irwin-Hall and Bates distributions start to look so much like the normal distribution. The higher I go, the more I'm summing or getting the mean of these uniform random outputs, the more they start to resemble the uniform distribution. So we've talked about randomness in computer science and statistics and some related concepts that are the inputs to the different distributions within d3-random. We also touched on a couple ideas, namely the law of large numbers and the central limit theorem that are pretty core to statistics and can be represented by some of these visualizations. There's a couple of cool ideas that I thought would be interesting to share, but we don't really have time to get into. I think what I just wanted to show here is how deep this topic can go and how d3-random kind of makes this bridge from visualization into statistics and mathematics. So if you look any of these up, I think they're pretty fascinating topics and I'd love to chat about them if you'd like. So thank you very much.